Hello, everyone, and welcome to the Lux webinar, the Global Hydrogen Trade, comparing developments in the EU, the US, and globally. My name is Mike Coleman. I'm a SVP and Group Director here at Lux, and I'll be the moderator today on this very exciting topic, one we've been generating a lot of questions and discussions from clients and in the overall energy and climate tech ecosystems here. And I think there's probably nobody better to share a perspective and to teach us all about that than Ari van Berkel, who's also SVP and Group Director leading the energy team here at Lux Research. So before I turn it over to Ari, a bit of housekeeping. You can type questions into the questions box on your screen at any point during the webinar. We will have some time for Q&A at the end, and we'll get to as many of those questions as we can. But if we don't get to yours or you come up with a great one afterwards, don't hesitate to email us at questions@luxresearchinc.com, and we will get back to you. So without any further ado, on to the presentation.
All right, thank you, Mike. And yes, hydrogen, it might actually happen this time around, right? Back in, I believe it was 2006, might have been 2005, when I was working at a contract research organization. We were debating whether we should pull out of a number of projects. There were lots of EU projects at the time about hydrogen, and we've been in them for maybe already a decade, and we were highly doubting if this would ever become something meaningful, right? There were, at the time, Europe was developing hydrogen islands, and I bet you never heard of one of those again. So here we are again, hydrogen, everyone's talking about it. Will there be a global hydrogen trade this time? We'll be looking into developments in the EU, in the US, and we'll pay some attention to global developments. And more importantly, we'll see how hydrogen could actually, this time around, become a reality. And I do believe it's a necessity in the energy transition. So without further ado, let's take a look at what's going on. And the first thing to look at then would obviously be the Inflation Reduction Act in the US. So Inflation Reduction Act, also known as IRA, of course, is mostly a tax reform, an amendment to the tax code in the US as far as renewable energy is concerned. There are some other elements to it that will generate the money that's being invested in renewable energy and decarbonization, things like carbon credits and carbon capture and storage. And an important part is a tax credit for hydrogen. If you look at the text, you can get a tax credit. And I should make this clear, a tax credit is not the same as a tax deduction. So even if you do not pay any taxes, if you're one of those unfortunate companies that doesn't make any profits, you can still get money from the IRS in the US. So you can get a tax credit. Depending on the CO2 intensity of how you produce hydrogen, the tax credit can be as high as even $3 per kilogram of hydrogen. In order to get that, you have to fulfill certain other requirements, for example, about how you pay your people, where you get the raw materials, etc. That will make a factor of 5 difference in the tax credit. Now, these numbers have been studied, for example, by the REPEAT project, which is a project at Princeton University. And they estimate that this could drive up to $170 billion of investment in hydrogen production. Now that's all nice, but of course we want to know how much hydrogen that actually amounts to. Well, to get to such a low CO2 intensity, you have to source renewable energy for the hydrogen production. And of course, you can source that from, say, solar, which would get you a capacity factor for hydrogen production of maybe about 30%, 35% if you're lucky. Or you could source it from hydropower, which could get you capacity factors even exceeding 80%, but I put 80% here on the slide. So you can see roughly what that kind of investment, what kind of annual production of hydrogen that could amount to. And if everything is connected to solar, it would be roughly 10 million tons of hydrogen. If everything would be connected to hydropower, it would be 28 million tons of hydrogen. In reality, it will be somewhere in between, let's say, 15 to 20 million tons of hydrogen. So the US, through the IRA, is set to deploy capacity for about 20 million tons of hydrogen per year. And that's low carbon hydrogen, so not the gray hydrogen that's already being produced. So what about the EU? Well, the EU had a policy called Fit for 55, which was designed to create demand for at least 7 million tons of hydrogen by 2030. And you can see roughly how that demand is broken down here. Following the war in the Ukraine and the need to have an accelerated energy transition in the EU, at least that's how the need to be less dependent on natural gas, and specifically natural gas from Russia, was interpreted in the EU. Fit for 55 was upgraded to the Repower EU package. And Repower EU aims to create demand for about 20 million tons of hydrogen per year by 2030 across the EU. You'll notice that there's a big portion other, which could also mean we don't quite know yet where this additional hydrogen demand will come from, but we'll figure it out by 2030. So if the EU needs 20 million tons of hydrogen, where does it get that? Because hydrogen, and the reason back in 2006, the hydrogen economy didn't happen, even though people were fervently working on it. Hydrogen has a chicken and egg problem. There's not enough supply of hydrogen because there's not enough demand. There's no investments in demand for hydrogen because there is no supply being announced. So you have to break the cycle, and that's why we're talking about governments in this webinar, right? Governments are taking action here because governments are very well positioned to orchestrate and to break those typical strangleholds of the chicken and egg problem. So where does the EU get the 20 million tons? Well, originally in Fit for 55, the plan was to just generate hydrogen within the EU, local production. And 7 million tons of hydrogen production within the EU is not crazy. It could be done, for example, using North Sea offshore energy. However, 20 million tons of hydrogen per year is a little bit crazy for EU terms. The EU needs hydrogen because it needs to import renewable energy. And therefore, the 20 million tons will, according to Repower EU, come 10 million tons produced locally within the EU and 10 million tons produced outside of the EU. And now you can see that the EU is also working to close all sorts of agreements with other nations, nations that have a lot of, for example, solar or wind potential, in order to create terminals and import capabilities for hydrogen from those countries. And you could think of countries like Saudi Arabia, Australia, Chile, all of those kind of nations. The EU does, however, want to export electrolyzer capacity. So it also wants to generate its own capability to manufacture electrolyzers so that even when hydrogen is being imported, the EU can still be the supplier of the equipment. And just to give you an idea about the domestic, the local production for within the EU, there are places like Spain and France that have abundant solar energy and wind energy. You will notice that both Spain and France have long coastlines and have a lot of ability to deploy offshore wind energy as well. But obviously, if you've been there maybe on a vacation, you know that Spain has more than enough solar potential as well. Heavy industry in Europe is concentrated in a band that runs from northern France and the Low Countries through Germany to northern Italy, roughly. That's where there's a big concentration of heavy energy intensive industry historically and still today. So you'll see that the heavy industry band will be importing from other places in Europe, for example, from France and Spain. And that's actually already being deployed right now, as there's a project called H2Med, Med for Mediterranean, which is building 2 pipelines with a combined length of about 700 kilometers to move hydrogen from Spain through France and towards Germany, and also from Portugal. And it's not hard to imagine that that pipeline could cross the Mediterranean and get into Morocco, for example, and start also using the solar potential in Northern Africa. And that's an active debate as we speak right now. You may have heard about the deal with Tunisia about migrants that the EU closed. In those conversations, renewable energy plays a role as well. So EU and the US are on very similar tracks when it comes to scaling hydrogen, of course, for very different reasons and with very different instruments. And that's important to note, because you don't know if the capital that is required is actually being mobilized, right? These are plans. Now the governments need to create private sector funding for these plans. And the US is doing that through a tax credit, which is simple, but not very flexible, but very simple and very easy for companies to understand and to count on. The EU is doing more complicated things, more open-ended, which means that it's much more flexible in terms of which technology gets deployed, but also it's much harder to mobilize private sector funding that way. If we look at the plans, the US is starting to approach about 20 million tons per year of hydrogen production by 2035. The EU needs about 20 million tons per year by 2030. The US is looking at about $175 billion investment by 2035, whereas the EU is building electrolyzer manufacturing capacity that could support about 150 billion euro investment in the years 2025 to 2030. So as you can see, very similar plans and very large quantities in both countries. If we look globally, and at Lux Research, we look globally also at the news. We track all of the news announcements, and we look at them on a quarterly basis to see what's happening. And as you can see, in the area of hydrogen for generation, but also the various applications for hydrogen, most news announcements these days are either about projects or investments or about partnerships. So this tells us everyone globally, not just the US and the EU, globally, people are in execution mode. They're trying to build things when it comes to hydrogen. Also noteworthy here is when it comes to projects and partnerships, there's a lot of emphasis on mobility as one of the applications for hydrogen. Which brings us to the question, what will all this hydrogen be used for? So we looked at production and generation. We looked a little bit at the EU wanting to consume 20 million tons of hydrogen. What are the use cases? Why would you want so much hydrogen? And how do you justify it? What's the business behind, and how will that develop? We'll spend the rest of the webinar discussing that, and we'll look at four generic types of applications: energy transmission, transportation fuels, high temperature processes, and petrochemicals, and they're connected. So I won't make a clean break between all of these applications. I'll try and give you some structure, but you'll see that they're fluid. These are not clearly separated application areas, as you'll see in a moment. And we'll start with transmission. Now, transmission is important because a place like the EU as a region needs to import renewable energy. It doesn't have enough renewable energy potential to generate all of the energy it would need for its current economy within the EU itself. And the same applies to Japan and South Korea, for example, and to a lesser extent to China. So it's important to move energy around globally, renewable energy, and one of the main ways to do that would be hydrogen. But even if you're not looking at that, it's still important to transmit energy and to have a way to concentrate energy. Fossil energy, whether it's a power generation plant, right, a combined cycle gas-fired plant, for example, or just a burner of fossil energy, like a massive glass furnace, for example, those type of installations typically have a power density of about 1 gigawatt per square kilometer. Heavy industry, like a steel mill or a refinery, consume roughly 50 megawatt per square kilometer. And that's never a problem because fossil energy provides a very dense source of energy. Renewable energy, on the other hand, if you look at offshore wind, for example, provides only 1 to 4 megawatt per square kilometer. You will find people saying, oh, no, we're already designing for 8. And that's true, but that's 8 megawatt per square kilometer without factoring in the capacity factor. If you factor in the fact that there's not always wind, then you have to more or less divide those numbers by half and you end up with 1 to 4 megawatt per square kilometer. That means in order to support infrastructure as the industry infrastructure as we know it today, you have to concentrate the energy that renewables provide by at least a factor 10. And hydrogen could play an important role to do that. Another way to look at it is to look at land-dependent industries versus just fossil-dependent industries that do not depend on any significant land space to produce the energy and the raw materials. So if you look at ethylene production, which of course is completely a fossil industry product, it processes, this is the site at one of the cracker sites in the Netherlands, processes about 1.5 million tons per year of carbon, right? 1.8 million tons per year of product. If you look at a paper mill, and especially a pulping mill that processes wood, therefore has a raw material that needs to come from the land, it processes about 122 kilotons per year. So about a factor of 10 less carbon per year and 250 kilotons of product per year. And of course, the product is more because biomass tends to have a higher oxygen content. Potato starch, very similar. It comes from the land. It is a highly efficient crop, but still the carbon processed is only about 270 kilotons per year, which is still a factor roughly 5 less than what you get with a pure fossil production unit. So in a renewable energy world where everything relies on land space, everything being both the energy and the raw materials, where we cannot get a concentrated source of carbon or energy that's coming from a well in the ground. In such an industrial landscape, you will likely get smaller industrial manufacturing units. However, today we have the big ones. So that raises a dilemma. Do we want to preserve the large production units or do we want to decentralize? And hydrogen is at the core of that dilemma, is part of the solution to that dilemma, which way to go. So one way to concentrate is to use the existing natural gas network. And here's an example of a company called Diddy Gas that's developing a way to introduce hydrogen into the natural gas network and selectively take it out again at the point of use. So in this case, they develop hollow fiber membranes. So you can blend hydrogen into the gas network. Today, it's considered safe to do that up to about 20%. And then you can take hydrogen selectively out at the point of use. Now, they're not quite at 20%. They can go as low as 35% today, but they're working to improve the technology. And meanwhile, the gas grid operators are working to increase the safe limits for blending hydrogen. So, getting back to the global trade, how would the global trade work? Well, you need a carrier, you need a way to move hydrogen around. And currently, the most considered carriers are liquefied hydrogen, so cryogenic, ammonia, or liquid organic hydrogen carriers, also known as LOHCs, which I used here because that's a lot shorter to put on a graph, of course. And as you can see, the cost of transporting hydrogen through any one of those carriers is pretty much the same. So there's not really a technical answer to the question which carrier is better. So at the end of the day, we believe that really this is a standardization problem. The first terminals that get built at a large scale will be setting a standard for the hydrogen carrier. So if the first terminals happen to be cryogenic, then liquefied hydrogen stands a good chance of scaling and becoming the carrier of choice. On the other hand, if liquid organic carriers are the first terminals to be built at scale, then that particular carrier has a good chance of becoming the carrier of choice. Ammonia is special because ammonia, you can see that the cost of turning ammonia back into hydrogen is significant, is roughly half the total cost of the carrier. So if you could use ammonia as is without having a particular desire to turn it back into hydrogen, it could be much cheaper. And this puts ammonia at an advantage. So on average, carriers would allow you to export your hydrogen to places where renewable energy is about $60 per megawatt hour more expensive. If ammonia can be used directly, you can export to places where renewable energy is about $25 per megawatt hour more expensive, which of course is much more, is a lot, much bigger markets. So a lot of people are already working to make use of ammonia directly in an engine. And of course, that's the largest group of people. And you should imagine those could be large marine engines, for example, two-stroke engines. Using it in a turbine is not so easy because in a turbine, it's very difficult to handle the NOx emissions, or in direct fuel cells. And of course, people are also working to burn ammonia. And burning ammonia without excessive NOx emission is actually possible and not even very expensive to do. But you do have to have a very good understanding of the combustion process. So that brings us, and I told you, things are blending a little bit. So now we're moving over to high temperature processes. And what you can see here is a US 2018 census on energy use in industry. And you can see energy use broken down here by the typical temperature range that the industry uses. So for example, glass manufacturing uses a temperature above 1000 Celsius. So it's in the ring at the top left of this picture, the over 1000 Celsius ring. together with steel and cement manufacturing, for example. The ring shows all of the different energy sources that the industry uses, not necessarily just for heat. So you can see that in glass manufacturing plus steel plus cement, there's electricity use as well. Those companies don't use electricity to generate heat, but they use a significant amount of electricity nonetheless. You can also see that a lot of other fuels are being used. Other fuels tend to be fuels produced by the industry themselves. So in the 500 to 1000 Celsius buckets here, there's a lot of refineries. Refineries tend to produce their own fuels, which is then labeled other here. Roughly 75% of industrial energy use in the US, and I think that's pretty representative for global energy use as well. That's industrial energy use, not all energy use, occurs in industries that require very difficult, like over 500 Celsius, or somewhat difficult, like between 180 to 500 Celsius, to electrify heat. And therefore, burning ammonia to generate heat, for example, or burning hydrogen to generate heat is a relatively accessible, early potential application of hydrogen at a large scale. So what about all those mobility projects? Remember, in our Niels analysis, a lot of projects were focusing on mobility. Well, let's compare an electric van, in this case a Renault van, with a hydrogen van. You can see the metrics here. If we do a quick calculation, and let's say we are running these vans 24/7, we are having shifts of drivers on them, so we're really trying to maximize utilization. Now you could say, well, if these are driving around at an average speed of 25 miles per hour, with an electric van, you would need 2 hours of charging for about 4 hours of driving. So the utilization could be about 65% maximum. For the hydrogen vans, you could do 5 minutes of charging for 10 hours of driving. So basically fill it up for every shift and then go. That would put the maximum utilization at about 99%, or for all intents and purposes, 100%, which would mean that in ideal circumstances, and circumstances are rarely ideal, you could buy 2 hydrogen vehicles to do the job of 3 electric vehicles. And given the difference in price, in purchasing price for these, that's a very precarious business case, which means that hydrogen is basically too expensive for transportation. If you do want transportation for hydrogen, you need government intervention. And we have a lot of examples where governments have used taxation, tax measures, and those kind of things to modify, to mold the fuel mix on their streets. Right? European governments have a rich history of changing the tax rules so that there's a mix of diesel and gasoline cars on the roads in order to support the product mix of refineries, for example. So that's entirely possible, but if you're curious about hydrogen mobility, look for government support, look for some sort of government aid for hydrogen. And I would look for that in Japan and Europe rather than in the US. Finally, we need to talk about chemicals and fuels. Hydrogen as a feedstock, right? If you have hydrogen, you combine it with carbon, let's say in the form of CO2, you can make all sorts of interesting products like methanol or like jet fuels. So, and then of course there's some products in here that depend just on CO2 and don't require hydrogen, like precast concrete, for example. So we did a very extensive analysis at Lux Research about the potential for such production. And our conclusion was that the tipping points for these type of CO2 to chemicals or CO2 to fuels type of processes, those tipping points are about 10 to 15 years away still. So there will be a large future market. Look at jet fuel, for example. It's a very large future market, potentially for hydrogen, but it will take about 20 years for that market to become competitive with the incumbent jet fuel market. So summarizing, hydrogen is a good way to move renewable energy, both concentrate renewable energy and move renewable energy between countries and regions. A lot of hydrogen is focused on mobility right now, but that's a precarious business case, and therefore you need to watch for government aid if you're betting on that. But industrial use will initially be driven by heat, and that is a much less precarious business case and could be really interesting in the short term. If you're looking for chemicals and fuels, it will take another 10, 15 years before those become a reality. Right, with that, let's quickly turn to the questions. There must be some debate in the audience.
Indeed, there's quite a bit. Thank you very much, Ari. And you can keep typing those into the questions box on the screen. And I can tell already we won't get to them all, but if we don't get to yours, we will follow up after that. So I think an interesting one to start with, Ari, is you kind of talked about this mismatch between the energy density of industry versus renewables. So someone asked, in the longer term, do you see an industry moving closer to the source of energy rather than the effort to move the energy to the existing industries?
Right, yeah, that's a very tough question to answer right now. There's the problem is, you could say, well, if it only depended on energy, sure, industry should probably move to where it's cheapest, where energy is cheapest. Why move the energy around if you can move the products around, especially if energy is as difficult to move as hydrogen or electrons, for example. However, it also depends on things like carbon. Where's the carbon coming from? And a lot of places that have cheap renewable energy, like say a desert, right, the Australian outback, have a market lack of chimneys. There's not a lot of CO2 being produced over there right now. So then you are quickly turning to the question of direct air capture, which is very expensive at the moment. So really, to answer that, I think it will be a mix. There will be, for example, looking at Europe or the US, I think both those places will export less chemicals. So a lot of the chemicals production, petrochemical production or hydrocarbon production will occur closer to the market. But at the same time, I do believe that they will, for domestic, for their own domestic use, still produce a lot of the hydrocarbons locally, because it ties in nicely with recycling, for example. Recycling will be one of the main point sources of CO2 in the future. So there'll be a mix. It won't completely move away, but there will certainly be a change in, let's say, the production centers of the world for energy-intensive raw materials like steel, cement, and plastics.
And maybe, I know we are coming up on time here, but maybe one more quick one. You suggested ammonia is going to be one of the dominant methods of hydrogen transportation. What about the safety issues with ammonia?
Yeah, safety issues for ammonia are not trivial. Ammonia is dangerous, and it's definitely more dangerous than, for example, gasoline or diesel. And you can see that in safety regulations, like in Europe we have the Seveso regulations, which draws contours around the installations based on quantitative risk assessment. The US, Japan, South Korea, they all have similar legislation. And within a certain contour, you cannot do certain activities. For example, you cannot have schools or hospitals, which means that ammonia is mostly a spatial planning issue. For example, the Port of Amsterdam announced that they will not be Why? Because they literally have no space for it. They cannot create the safety zones around it. For example, is already accustomed to it. They already have ammonia terminals. So it really depends on where you import ammonia, and I'm sure we'll find places to do that. And then it becomes an engineering problem. Literally handle with care.
Yes. All right. Well, thanks, Ari, and thanks to all of you for joining us. That's all we're going to have time for on the webinar today, unfortunately. But we will be sending the slide presentation and recording around to all the attendees by email within the next 24 hours or so. When you leave the webinar, you will get a prompt to complete a survey. We really appreciate taking just a couple of minutes to fill out that short questionnaire. We do look at those very closely and use them in informing and improving our future webinars, which you can, I think if we advance, can check out on the screen here. Some very interesting upcoming ones on robotics in agriculture, the UN plastic pollution plan, decarbonization policy, and more beyond that as well. But thank you all for joining us, and have a great rest of your day.